what created all these companies like Micromax. In fact, just IPL was created. Huh? Oh, okay, fine, that's okay. So IPL created these big companies. Working. So why don't you restart it? Oh, you don't want to do that? Okay, fine. Okay, let's start. So what we will do today is we'll just go back and recap what we did in the previous lecture and try to understand what's going on. Okay. We start with this model. R transmit, T receive, or T transmit, R receive, the other way. This is a general system model. We derived the capacity of the channel for this model is equal to Hx plus n, and it turned out that to achieve capacity, the transmitter needs to know H exactly, or either H or the eigenvalues of H as well as the eigenvectors of H Hermitian. So H is UD V Hermitian and the number of non-zero eigenvalues of D is minimum of R comma T. Okay? It's the number of non-zero eigenvalues or the number of streams that the channel can support. That is, we have a transmitter where we apply some Vn as a beamforming matrix. N is arbitrary, we'll discuss that. And then you transmit this, the signal X. Okay? The input, you may call it X multiplied by Vn or maybe X2, something like that, or X tilde maybe. X equal to Vn X tilde. Okay, what is this Vn? Vn could be V, but then you are transmitting T streams. Okay? If Vn is a T by T matrix, then you have to transmit T independent data streams. Okay? So instead what we can do is, you can choose that way and then do power loading, but on the other hand, we can choose Vn from this V, where V is written as V1, V2, up till, these are the columns. How many columns are there? T by T, so T columns are there, right? There are T columns. So you can choose any number of columns from this V matrix as the beamforming matrix. If you choose 1, then the dimension of X tilde becomes 1. It becomes a scalar. Then we call it single stream beamforming. If you choose n equal to 2, you send 2 streams with a beamforming matrix of V1, V2, 2 streams. You can perfectly recover them. We will show that, right? In fact, we'll see that. If we send V1, V2 up till V minimum of R comma T, if n equal to min of R comma T, Vn somewhere, then you can send that many streams, and at the receiver, you can perfectly recover them without crosstalk. Okay? So, then you may ask us, well, we do know that the capacity achieving structure definitely sends min R comma T data streams, and it will also allocate unequal power for the elements of X tilde using water filling, and elements of X tilde are chosen from a Gaussian codebook which achieves capacity. Okay. However, in practice, you may apply separate modulation and coding on different elements of X tilde, X tilde 1, X tilde 2. They are separately encoded and decoded because they are parallel data streams. Okay. So, essentially, this transmit beamforming or VN, putting this VN here, and using a receiver with U Hermitian, the combination VN at the transmitter and U Hermitian at the receiver simply diagonalizes the channel and it converts a matrix channel into a series of parallel scalar channels. Okay, let's go through this once more. Y is equal to Hx plus n, and H is U dV Hermitian x plus n let's apply U Hermitian Y, where U Hermitian is the receive filter. It's called receive beamforming filter. This is maybe called transmit beamforming filter. Okay. That would be equal to U Hermitian, U dV Hermitian, and x equal to Vn x tilde plus U Hermitian n. Okay, that gives us d V Hermitian Vn x tilde plus n tilde. Okay, and then let's see how we recover our individual data streams. Like I said, Vn where n could be range from 1 to min comma r comma t, min r of rt. So D is a diagonal matrix, lambda 1, lambda 2, up till lambda n, and then possibly zeros elsewhere. Right? V1 Hermitian, I write V Hermitian as V1 Hermitian, which is a row, V2 Hermitian, another row, up till Vn Hermitian, up till the last element, which is Vt Hermitian, because this is a T by T matrix. These are the rows. Well, Vn is V1, V2 up till Vn, and then x tilde is x tilde 1, x tilde 2 up till x tilde n. Okay, V being a unitary matrix, the rows of V are orthonormal. Okay, therefore this is 1 by T, this column is T by 1, and the product is V1 Hermitian V1 is 1. It's orthonormal, it's scaled. So what we get here is lambda 1, lambda 2 up till lambda n, and then all zeros. It's not lambda n, but it's lambda min r comma t, lambda min r comma t. Then what do we get here? It's a 1 here, and then zeros. Again 0, you will get and then up till Vn Hermitian you will get an identity matrix and then zero rows elsewhere and then all zeros elsewhere and this would be x1 tilde, x2 tilde up till xn tilde plus n tilde. Well, now if you write, let's call it y tilde. Now it should be straightforward to see that y1 tilde would be lambda 1 x1 tilde plus n1 tilde and then up till yn which is lambda n xn tilde plus and then zeros the signal component is 0 and only noise will be left. So it's up to you how do you choose n. Okay, the capacity achieving structure choose n as min comma r comma min of r comma t and then you do water filling, you achieve capacity. But on the other hand, either the receiver or the transmitter can decide how many streams they want to transmit. Okay, you may ask, why do you want to reduce the number of streams when you can have min r comma t? Well, it depends that, if you want to instantaneously change the number of streams depending on the channel, sometimes some of the eigenvalues may be small and you may not want to send max number of streams. Okay. So the question is, are all the antennas utilized? Well, they are utilized, right? The number of streams is less than the number of antennas, but it doesn't mean that some of the antennas are discarded. Whether you send one stream, two stream, or what is the dimension of Vn? T by this is T by n. This is n by 1. So all the antennas are utilized, right? So when you reduce the number of streams, if you have more antennas than the number of streams, the remaining antennas are used for beamforming. What does it mean?
So here n is the minimum of R and T, right?
Yeah.
So if n equal to R and R is less than T.
If n equal to R
And R is less than T.
R is
Less than T. R is less than T means n equal to R, right?
then you choose R.
So
R streams.
here it will be T by R into R by 1. It's R by 1.
T by R into R by 1. But T is greater than R.
We have only R streams.
R streams.
So R antennas are used, right?
No. T antennas are used. Okay. Why don't we take a 2 by a system with okay, I gave you single stream example, right? How many antennas did we use? All antennas. What did we do? We put weight such that all the energy is coherently combined. Right? That was easy to see. Do you want me to go through that example again? No. Okay? You have two antennas at the transmitter. Instead of sending two streams, we sent one stream. So all the antennas are used to give what is called array gain. It's not spatial multiplexing gain, but it is array gain. Let us take 4 transmitting antennas and send 2 streams and see how it works. Okay? Let's work with an example. Okay. T equal to 4, n equal to 2, and R is greater than or equal to 4. Where R could be even greater than or equal to 2. Minimum unit is 2. Okay? In fact, the R doesn't even come into picture here, right? I mean, it's n and t. Okay? So, the matrix Vn is V1, V2, but this is a 4 by 1 vector and this would be a 4 by 1 vector. This is a 4 by 2 matrix. And x tilde is x1 tilde, x2 tilde. Well, I think yesterday I called it Vn into x as x. Okay, but that's okay. It's just a notation. So let me erase this. Y is equal to h Vn plus n. This is what is transmitted. Okay? So this can be written as V1 x1 tilde plus V2 x2 tilde plus n. So what is transmitted is a linear combination of x1 and x1 tilde and x2 tilde with these vectors multiplying them. And size of this vector is
4 by
okay. So you may wonder, if I increase t to 8 and 10 and 20 arbitrarily, what is that I get? Okay? What is that I get? Well, in single stream transmission, this was absent. And when I have single receive antenna, the array gain was a factor of t. And the number of antennas was the array gain. But the notion of array gain, when you have a two stream transmission, is a little more complicated. You can't put a number on it. Can't put an exact number on it. It depends on the number of receive antennas as well as the number of transmit antennas, and you don't get this perfect array combining in multi-stream transmission. Okay, you don't get this perfect array gain. I think you should simulate and see it. You don't get this perfect array gain in this multi-stream transmission. Okay, to illustrate that, we'll go back to single stream and have two receive antennas. Okay, to illustrate that, we'll take single stream transmission and have an arbitrary number of receive antennas. To give a physical analogy, let's take a single stream transmission, and then we'll work with this. The transmitter has a number of antennas, and these antennas are trying to point a strong beam to one receiver somewhere in the direction. So you can measure the path gains from each transmit antenna to the receiver, put a spatial match filter, and then you put a strong beam towards one receiver. And as the number of transmit antenna increases, the beam forming gain increases. But let us say the receiver has two antennas, and one is here and one is here. Now, the transmitter can only beam form and point to one point in space. Should I put the strongest beam to that antenna or this antenna? I have a torchlight. I can only put a beam towards one point. If you have two receive antennas, what should I do? Well, I probably put somewhere in the middle. Okay? So your array gain reduces. If you have two transmit, two receive, although you are sending single stream beam forming, your array gain reduces. The reason is that you can't put a single sharp beam to any one point. Let's say you put a third antenna in that corner and fourth antenna in that corner. Where should I put my beam? In the limiting case, as the number of antennas increases arbitrarily, the array gain vanishes. Then what you should do is you shouldn't put a beam, you should radiate uniformly in all directions. So there is no array gain. Instead of looking at this mathematically, that's probably the best way of explaining it. You can show that even mathematically, as the number of receive antennas increases arbitrarily, and transmitter is sending a single beam, a single stream, but you lose your array gain completely. Why is that? Is that an anomaly? Well, it's not really an anomaly. What you should have done was, well, first of all, you get a diversity gain. As the number of receive antennas increases, you get receive array gain, and you get your diversity gain will be a product of number of transmit and receive antennas that you can show. If you have a single stream, if you have NT and T antennas and R receivers, T multiplied by R is the diversity advantage. Okay, but array gain is lost. But then you may be wondering, why is that is the source of optimum? Well, I think you should have done spatial multiplexing, because when you have so many receive antennas and when you have so many transmit antennas, the better thing to do not to form strong sharp beams, which only gives you an array gain, which is an SNR advantage, and log of 1 plus SNR can only take you so far because the SNR is inside the log. What you should do is a pre-log multiplicative factor, which is the spatial multiplexing gain. That is, you should put multiple streams, find the eigenvalues of this big matrix, send multiple streams, and get spatial multiplexing gain, rather than shoot for the beamforming gain, which is the SNR improvement. So, in minimum of R comma T, log of 1 plus SNR kind of formulation, it's futile to increase the array gain by improving the SNR. Array gain is an improvement in SNR, because log kind of damps it, so the total rate increase is quite limited. Rather, you should multiply this with minimum of R comma T, which is a multiplicative increase, pre-log increase, which is much more higher, which is quite substantial, especially in the high SNR regime. So, to cut the long story short, these transmit antennas do play a role to increase the beamforming advantage, or so-called array gain, when you limit the number of streams to 2 and have higher number of antennas. But that benefit is quite marginal. The real rate increase is given by the number of streams. Okay? So what you can do is, you can take 2 transmit 1 receive, 2 transmit 2 receive. This is transmit, this is receive. 4 transmit 4 receive, 4 transmit 1 receive, 4 transmit 2 receive, and just calculate the capacity. You don't have to do a bit rate simulation. You do eigen decomposition, calculate the capacity, and plot capacity versus SNR, and the y-axis should be expected value of C, and this is SNR. And how do you calculate this? Well, simulate a number of H matrices and average it, and then you can see the various trade-offs. This is easy to do. There is no bit rate simulation involved. Generate different H matrices using IID, complex Gaussian entries, and calculate the capacity using the framework we developed. Okay? Through simulation, you can see what's going on. In fact, you can analyze these things in closed form or using some approximation, but it's quite cumbersome. Okay? The mathematics involved is quite complicated. At least for the time being, you can just simulate it. So deal with the random matrices and stuff like that. Okay? I think when you simulate it, you'll understand this a lot more. Okay, so this is the story with the knowledge of channel state information at the transmitter. Either transmitter knows H fully, or it knows the eigenvalues and some of the eigenvectors of V. What if transmitter doesn't know anything? Can we achieve this capacity? That's a tall order, right? We have this V here, we have that U there, which did bulk of our job, right? In fact, the transmit receive architecture is overly simplified. All you have to do is now bring the coding into picture. That's all, right? You have to encode each of these scalar channels and achieve the capacity. That's all. The signal processing part is quite simple. Once you have the V and U. Okay. Now the question is, can you achieve the same capacity or a significant part of this capacity without knowing the channel at the transmitter? Is it possible? Think about it and let me know. Well, it turns out that you can achieve pretty much most of this capacity given by the channel without having knowledge of H at the transmitter. Well, that sounds like a fairy tale, but you get pretty close to this capacity without knowing the channel. Okay. Why is that? Well, we have looked at spatial multiplexing with MMSE receivers, and we did show a pre-log min R comma T scaling, right? Did we? We showed something as simple as sending T streams with R receive antennas with the T less than R, with T less than R, each MMSE receiver was able to get rid of self-interference, and thus the post-processing SINR of the MMSE receiver was growing at the rate of 1 over N naught, and therefore log of 1 plus SNR was the, right, some sort of SNR was the capacity of each stream, and there are how many streams we could support with full interference cancellation? Min of T comma R. See, there is some connection, right? The only thing that MMSE framework cannot support is the additional beamforming, but that you can always incorporate. See, the min R comma T multiplicative factor is the big thing when you talk about spatial multiplex. Well, you may say, well, if I want to send single stream and if I don't have channel state information at the transmitter, then how do I encode the signal? Using T antennas. That is a non-trivial exercise. We'll leave it that special case for a separate discussion. Arbitrary T, n equal to 1, no channel state. How do you encode the signal? That is highly non-trivial, okay? But as long as we have T equal to n equal to some number, and you have R receive antennas, R greater than T, then this is called spatial multiplexing. T transmit antennas, and you send T streams. N is the number of streams. N is number of streams. T is the number of transmit antennas. You make them equal and R is greater than or equal to T, then the MMSE receiver was able to perfectly separate these streams, and you have a practically working system. Fine, right? That's one of the reasons why I developed this MMSE receiver before talking to the capacitive channel. If I didn't develop this MMSE receiver, then how you could achieve this linear capacity growth without channel state information is right? It's hard to justify it. Just from information theory point of view, justifying it is a little difficult because the capacity expression doesn't tell you exactly how to achieve that capacity. In the presence of knowledge of H at the transmitter, you know how to achieve the capacity, right? But if you don't know H at the transmitter, we can derive the mutual information. That turns out to be okay, what are the dimensions? H is R by T, T by R, this is IR. This is also equal to log of determinant of IT plus P by T H Hermitian H. Okay? This stands for determinant. How do you derive this? Well, calculate the mutual information for the system model. Y is equal to Hx plus N without having channel knowledge H at the transmitter. You can derive this. It's given in the Teletas paper. You can go through it. Otherwise, we can also derive it. It's not a big deal. Okay. The nice thing about this is, you have seen something like this when the transmitter knows H. Where was it? Well, let's see. This can be written as summation over log base to 1 plus P by T lambda I, where I goes from 1 to min R comma T. How is it possible? Well, determinant of H Hermitian or H Hermitian H, determinant of a matrix is equal to product of determinant of a matrix is equal to product of eigenvalues, and you bring this one inside. 1 plus P by T is equal to product of it's inside the logarithm, right? And log of product is equal to, did we see this somewhere? Well, if you don't do water filling, and if you divide the transmit power equally among T streams, or in this case we call it the minimum of R comma T, but let's say T streams, this is practically close to the capacity with feedback. Only difference is water filling. Remember, for each lambda we had a different power through water filling, but here the power is same. So it's closely related to the capacity with full H. But how do you achieve this capacity? Well, we don't know. When H was available, we had V matrix at the transmitter and U Hermitian at the receiver. Boom, we are done. We got a set of parallel channels, and the problem is trivially simple. Then you encode each stream with separate modulation and coding. But here, I mean, we really don't know whether should we encode the different data streams together, or should be encoding them jointly, separately. We don't know. And what is the receiver that we should use? We don't know. I mean, it doesn't really tell you what sort of receiver you should use. Well, it turns out that something as simple as an MMSE receiver will not give you this capacity, but something close to this. There is a gap, right? An acceptable gap, and that gap can be bridged by using a little more receive antennas than the transmit, because MMSE receiver gives you a higher diversity gain. Right? And there is another receiver, what is called a maximum likelihood receiver, that works with this model, that jointly detects the modulation alphabets contained in the vector x. How do you implement that? The decision rule for detecting x hat is minimize y minus hx Hermitian y minus hx. What is that? That is the distance between, this is x hat over all possible candidate x hats. How many candidates are there? If x is a vector of size t, and each point in x, let's assume, has a constellation of size m, or let's say it's q. How many possibilities are there? Q raised to x belongs to a size set, x belongs to a set S, where cardinality of the S is q raised to t. When q is 16 QAM, 16 raised to 2 or 3 or 4, whatever it is. This is called a maximal likelihood receiver that can jointly detect all the data streams. And the nice thing about this is, now there is no limitation on the number of transmit or receive. You can have t transmit and even one receive is also possible. Well, it's a nonlinear receiver. It can perfectly, you can have 2 transmit and 1 receive, and you can still resolve 2 streams. Well, there is an SNR penalty you have to pay because you are sending more streams than the receiver can support, but you can nevertheless separate them. Well, you can think of them jointly encoding those 2 streams in space using a matrix. So, a maximal likelihood receiver will give you a performance better than the MMSE receiver we discussed, and in fact you can show that the diversity order of MMSE is NR minus NT plus 1, or diversity order for MMSE is R minus T plus 1, and when R equal to T, it has first order diversity, whereas this maximal likelihood receiver can separate all the signals, that is like full interference of signal separation, but nevertheless it gives you full diversity of order R. The difference between MMSE and MLD is, this gives you a diversity of order R, whereas this loses some degrees of freedom for separating signal because it's a linear receiver. This being a non-linear receiver, it gives you a diversity of order R. If you have 2 transmit, 2 receive, this can fully separate both received signals, and it gives you a diversity of order 2, whereas this gives you a diversity of order 1. Therefore, this receiver has a better performance and it has a higher chance of approaching this capacity. I'm not saying it would approach that capacity, but if you bring coding into picture, this is only a demodulation, right? And then you have to decode x1 and x, the elements of x, using a channel decoder. You can either separately encode the elements of x, or you can jointly encode them. That is, there is a channel code of rate R, and then you can split the output symbols and transmit them on different antennas. It's like a single code. Transmit them on different antennas, decode using MMSE or MLD, demodulate, and then decode using a channel code. Or you can have a separate code for these, for each stream, and decode them separately. But I think you are better off coding them jointly. And that depends on the type of receiver you are using. If you are using this type of receiver, since there is coupling between the elements of X, you are better off putting a single mother code and splitting them onto different antennas. But if you use an MMSE, since all the streams are decoupled, you can probably encode each stream separately. It's like having many sessions running in parallel, right? You can have voice on one stream and data on another stream. I mean, just to give a crude example. Whereas here, you can just have a single code and decode them together. Well, this is, we're looking at this in we're giving a very high level picture of MIMO here. I mean, there are a lot of details that are involved. If you have CSIT, problem is simple, encoding and decoding. the channel state information at the transmitter H. If you don't have H, then MMSE is one candidate with spatial multiplexing, or you can also have this so-called MLD receiver, which is considerably more complex, right? Okay. So this sort of concludes the discussion on MIMO, except for one little thing we have missed. That is, in fact, this transmittability of space-time coding was very hard some 10 years ago. There are thousands of papers on it. Of course, this is also a lot of papers on this, but this subject alone was quite hard for some time. That is, you send a single data stream. You can have any number of antennas, 2, 3, 4, and the receiver has possibly one antenna or two, any number. Preferably, the setting we are going to consider is more antennas at the base station and single antenna at the receiver, and it's a narrow band channel, and you want to give diversity. There is no spatial multiplexing involved here. How would you design a system? Okay, this belongs to the topic of transmit diversity of space-time coding. Okay, we need one more lecture at least to address this. That kind of concludes this course. Okay, so what I want you to do is I want you to simulate the performance of MMSE receiver with spatial multiplexing that belongs to the open loop class, and then I want you to simulate the performance of closed loop, which is the beamforming, with the knowledge of H at the transmitter, which is a fairly simple simulation because it doesn't involve bit error rate calculation. Anything that involves bit error rate, you have to simulate the whole link. But this is simple. So you can simulate these two and compare. All you have to do is compare the capacities of spatial multiplexing with MMSE and the capacity of channel with H known at the transmitter, and you can see how they compare with each other. Okay, and transmit diversity more or less I don't think we'll have a lecture, but no simulation exercise. Is this something you can do? Are you all done with the cyclic prefix business? Right? You're done. Now you know how it works? Yeah. And did you put the channel code in there? Yeah, just take help from these guys or anybody else. It's just an encoder and decoder. You just have to. It's a couple of hours job, not more than that. With 3 guys working on it, you should be able to do it in 2-3 hours. That's why I said work in groups. Okay? So you must get it done, the encoder decoder. Then these assignments have to be completed. Otherwise, I cannot assign you a grade. You must complete these assignments together with that. And everything should be done by 3rd. 3rd is Monday. I mean, this is the absolute deadline, but I prefer that you do complete these by Saturday or Sunday. I mean, there is some time. I'm leaving on the evening of 3rd, and I want to give the grades. Submit the grades on the 3rd, because there's no point in delaying it any further if I'm not around here. Okay, so let me just reiterate. MMSE receiver you have to do and calculate the capacity of the MMSE receiver, that is average capacity versus SNR, and compare that with capacity of channel without CSIT and with CSIT. CSIT means channel state information, that is H matrix, with and without feedback. The theoretical capacity with and without feedback, capacity achieved with spatial multiplexing. And you can choose the configurations. I will leave it up to you. 2 by 2, 4 by 4, 2 by 4. Just take some numbers. A maximum of 4 antennas at the transmit and receive ends. Okay, then there are some combinations. For spatial multiplexing, you need to do bit error rate simulation as well as capacity calculation. The rest are all capacity calculations. Okay? Okay, we'll stop it here today. So when would be the next lecture? I need one extra lecture where we could discuss, your assignments as well as, the leftover topics. See, I'm going to move to command today, so I will have to travel from there. So you have to take that into account. Friday.
Can you give it tomorrow? Because Friday we are confused whether there is lab or not. Because we already completed all labs.
Okay.
We'll mail you the time on Friday. Either it will be in the morning or.
Yeah, you let me know. See, I'm going to be in command, so command, I don't know what time the vehicle leaves there. Is there a shuttle?
Yeah, there's a shuttle.
Huh?
There's a bus in the morning,
What time?
8 I think.
Okay, and?
And then afterwards it's 9 or 10 something.
Okay.
Then there's another at 2.
Okay, maybe I'll take the one at 9 or 10. Okay? And it's a 45 minutes ride, is it? Okay. And evening, what time is the bus?
For you to come and to come.
If going from here to command.
7:30.
7:30.
6 and 7.
Only one.
No, there are 2, 3 buses. 5 also. At 5 also there is a bus.
5 also there is one. In fact, I have to leave today. Are you attending the college day today in command? Not college day, but hostel day.
Hostel is there.
You're not going there? Huh?
We have so many presentations and everything to complete this week.
So this is the last week, I see. And besides, you don't want to see them anyway. They are first year or second year?
Second.
You are fourth year, so you have nothing to do with them. Okay, all right.